Okay, hi everyone, welcome back to this video series on data centers. Class A valid host IDs. Here's an example of how to figure out the valid host IDs in a Class A network address. All host bits off is the network address 10.0.0.0. All host bits on is the broadcast address 10.255.255.255. The valid hosts are the numbers in between the network address and the broadcast address 10.0.0.1 through 10.255.255.254. Notice that zeros and 255s can be valid host IDs. All you need to remember when trying to find valid host address is that the host bits can't all be turned on or all be on at the same time. Class B addresses. In a Class B network address, the first 2 bytes are assigned to the network address and the remaining 2 bytes are used for node addresses. The format is as follows: network.network.node.node. For example, in the IP address 172.16.30.56, the network address is 172.16 and the node address is 30.56. With a network address being 2 bytes, 8 bits each, there would be 216 unique combinations, but the internet designers decided that all Class B network addresses should start with the binary digit 1 and then 0. This leaves 14-bit portions to manipulate. Therefore, 16,384, that is 214 unique Class B network addresses. A Class B address uses 2 bytes for node addresses. This is 216 minus the 2 reserved patterns, all zeros and all ones, for a total of 65,534 possible node addresses for each Class B network. Class B valid host IDs. Here's an example of how to find the valid hosts in a Class B network. All host bits turned off in the network address is 172.16.0.0. All host bits turned on is the broadcast address 172.16.255.255. The valid hosts would be the numbers in between the network address and the broadcast address 172.16.0.1 through 172.16.255.254. Class C addresses. The first 3 bytes of a Class C network address are dedicated to the network portion of the address, with only 1 measly byte remaining for the node address. Here's the format: network.network.node.node. Using the example IP address 192.168.100.102 and the network address is 192.168.100 and the node address is 102. In a Class C network address, the first 3 bits positions are always the binary 110. The calculation is as follows: 3 bytes or 24 bits minus 3 reserved positions leaves 21 positions. Hence, there are 21 or 2097152 possible Class C networks. Each unique Class C network has 1 byte to use for node addresses. This leads to 28 or 256 minus the 2 reserved patterns of all zeros and all ones, for a total of 254 node addresses for each Class C network. Class C valid host IDs. Here's an example of how to find a valid host ID in a Class C network. All host bits turned off in the network ID 192.168.0.100.0. All host bits turned on is the broadcast address 192.168.100.255. The valid hosts would be the numbers in between the network address and the broadcast address 192.168.100.1 through 192.168.100.254. private IP addresses, RFC 1918. People who created the IP addressing scheme also created what we call private IP addresses found in RFC 1918. These addresses can be used on a private network, but they're not routable through the internet. This is designed for the purpose of creating a measure of well-needed security, but it also conveniently saves valuable IP address space. If every host on the network had to have a routable IP address, we would have run out of IP addresses to hand out years ago. But using routable IP addressing, by using private IP addresses, ISPs, corporations and home users need only a relatively tiny group of bona fide IP addresses to connect their networks to the internet. This is economical because they can use private IP addresses on their inside networks and get along just fine. To accomplish this, the task, the ISP and the corporation, the end user, no matter who they are, need to use something called network address translation, NAT, which basically takes a private IP address and converts it for use on the internet. Many people can use the same real IP address to transmit out onto the internet. Doing things this way saves megatons of address space. Take a look at figure 5.2. NAT translation will be configured on the corporate router and translate public and private IP addresses for the company. The interface connecting to the internet would be real global IP address, and the addresses configured on the engineering and sales routers would be private IP addresses. It's very important to remember the following. Private IP addresses RFC 1918 are not globally routable on the internet. RFC 1918 specifies that networks must be reserved in each class. 1 network in class A, 16 networks in class B and 256 in class C. RFC 1918 was created to establish a range of IP addresses that are dedicated to use on internal networks. RFC 1918 was created to delay the transition to IPv6. The IP address must be filtered and internet border interface. Private address include 10.0.0.0/8.172.16.0.0/20 and 192.168.0.0/16. Network address translation is required on the internet border device. The reserved private addresses are listed in table 5.2. Address class, reserved address space. Class A 10.0.0.0 through 10.255.255.255. Class B 172.160.0 through 172.31.255.255. Class C 192.168.0.0 through 192.168.255.255. IPv4 address types. I've referred to IP addresses through chapters 1 and 2 and even showed you some examples, but I really haven't gotten into the different terms and uses associated with them yet. It's about time I did. So here are the 4 IP address types what I'd like to define for you. Loopback, localhost, used to test the IP stack on the local computer, can be any address from 127.0.0.1 through 127.255.255.254. Layer 2 broadcast. These are all sent to all nodes on a LAN. Broadcast layer 3. These are sent to all nodes on the network. Unicast. This is an address for a single interface, and these are used to send packets to a single destination host. Multicast. These are packets sent from a single source and transmitted to many devices on different networks, referred to as one-to-many. Layer 2 broadcasts. First, understand that Layer 2 broadcasts are also known as hardware broadcasts. They only go out on a LAN and they don't go past the LAN boundary router. The typical hardware address is 6 bytes, 48 bits, and looks something like 0C43.A4.F312.C2. The broadcast would be all ones in binary, which would be all F's in hexadecimal, as in FF.FF.FF.FF.FF.FF. Layer 3 broadcasts. Then there are the plain old broadcast addresses at layer 3. Broadcast messages are meant to reach all hosts on a broadcast domain. These are all the network broadcasts that have all host bits on. Here's an example that you're already familiar with. The network address 172.16.0.0.255.255.0.0 would have a broadcast address of 172.16.255.255. All host bits on. Broadcasts can also be any network and all hosts, as indicated by 255.255.255.255 unicast address. A unicast address on a single interface IPv4 in IPv4 you can have only one unicast address on an interface, and that address cannot be used anywhere else on the network. Multicast address. Multicast is a different beast entirely. At first glance it appears to be hybrid of unicast and broadcast communication, but that isn't quite the case. Multicast does allow point-to-point, multi-point communication, which is similar to broadcast, but it happens in a different manner. The crux of multicast is that it enables multiple recipients to receive messages without flooding the messages to all hosts on a broadcast domain. However, this is not the default behavior. It's what we can do with multicasting if it's configured correctly. Multicast works by sending messages or data to IP multicast group addresses. Routers then forward copies, unlike broadcasts, which are not forwarded, of the packet out of every interface that has hosts subscribed to that group address. This is where multicast differs from broadcast messages. With multicast communication, copies of packets in theory are sent only to subscribed hosts. When I say in theory, this means that all hosts will receive, for example, a multicast packet defined for 224.0.0.9. This is an EIGRP packet, and only when a router running the EIGRP protocol will read these. All hosts on the broadcast LAN Ethernet is a broadcast multi-access LAN technology will pick up the frame, read the destination address, and immediately discard the frame unless they are in the multicast group. This saves PC processing, not LAN bandwidth. Multicasting can cause severe LAN congestion in some instances if not implemented carefully. There are several different groups that users or applications can subscribe to. The range of multicast addresses starts with 224.0.0.0 and goes through 239.255.255.255. As you can see, this range of address falls within the IP class D address space based on the class IP assignment. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.